You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Threat modeling for applications provides a structured way to anticipate adversary behavior and design controls before attacks occur. Its purpose is to move security left in the lifecycle, ensuring that microservices and application programming interfaces APIs are built with defenses aligned to their risks. In cloud-native systems, applications are composed of distributed services connected by APIs, each with its own boundaries and dependencies. This complexity creates new attack surfaces and failure modes. Threat modeling makes that complexity visible, identifying assets that need protection, where trust transitions occur, and how adversaries might exploit weaknesses. By mapping threats to controls and detections, organizations can prioritize mitigations that matter most. For learners, the key is to see threat modeling not as an academic exercise, but as a repeatable discipline that produces actionable outcomes, aligning development with business risk and compliance obligations. Threat modeling is systematic rather than ad hoc. The process identifies valuable assets, maps entry points, enumerates plausible threats, and aligns controls for an application context. For example, a payment service might identify transaction data as an asset, define APIs as entry points, consider threats like replay attacks, and apply mitigations such as nonce validation. The systemization prevents oversight, ensuring that even subtle or less obvious risks are considered. It also ensures that security discussions are structured, giving teams a consistent language to describe risks and responses. Without this discipline, organizations risk patchwork defenses that leave critical gaps. With it, applications are examined holistically, producing consistent and repeatable results. Asset inventory is the first step, enumerating data, services, identities, and secrets that require protection. Assets can include user records, service credentials, and proprietary business logic. By making assets explicit, teams avoid focusing only on the obvious, while overlooking hidden valuables, such as configuration stores or audit logs. Each asset must be linked to its owner and its classification, enabling downstream prioritization. For example, customer personally identifiable information may require stricter access controls and stronger encryption than operational metrics. Asset inventory grounds the model, ensuring that threat analysis is aligned with what truly matters to the business. Trust boundaries define where control assumptions change. They mark the transitions between clients and services, services and data stores, or internal systems and third-party providers. Each boundary requires explicit controls, such as authentication, encryption, and monitoring. For example, when requests cross from an external client into a microservice, the system must validate identity and sanitize inputs. Without defined boundaries, implicit trust may creep in, leaving systems vulnerable to injection or privilege escalation. By drawing these boundaries early, teams can identify where security must be concentrated and where assumptions must be documented and verified. Microservices architecture complicates threat modeling by expanding inter-service communication. Each microservice may expose APIs to peers, creating new trust relationships and dependencies. These connections expand the attack surface, as vulnerabilities in one service may ripple into others. For example, a weakly authenticated internal API may allow lateral movement into sensitive domains. Versioning, service discovery, and orchestration also introduce failure modes that adversaries can exploit. Threat modeling microservices requires attention to identity for services, mutual authentication, network segmentation, and resilience patterns. It shifts the mindset from securing a single application to securing a constellation of interconnected services. API exposure is central to modern applications and requires careful scrutiny. APIs define the contract between services and clients, specifying operations, inputs, and outputs. Each endpoint must be documented with its authentication expectations, authorization rules, and allowable operations. For example, A public API may allow read-only queries, while internal APIs may permit state changes under strict authentication. Failing to document these assumptions leaves APIs prone to overexposure, privilege escalation, or abuse. Threat modeling ensures that APIs are governed explicitly, mapping exposure to intended use and applying safeguards consistently. Frameworks such as Stride provide structured categories for analyzing threats. Spoofing considers identity deception, tampering involves unauthorized changes, repudiation challenges accountability, information disclosure risks data leakage, denial of service disrupts availability, and elevation of privilege expands unauthorized access. For example, Stride applied to an API may highlight spoofing through token theft or DOS through unthrottled queries. Categorization ensures that threats are not overlooked and that mitigations are balanced across types. It also simplifies communication, allowing stakeholders to see the breadth of risks addressed. Privacy threats deserve equal attention, addressed by frameworks like LINDDUN. Linkability, identifiability, and detectability highlight risks of user re-identification. Disclosure considers data leaks, while unawareness and non-compliance address consent and regulatory violations. For instance, analytics APIs may inadvertently enable identifiability if anonymization is weak. Threat modeling that includes LINDDUN ensures that privacy risks are not sidelined but treated as first-class concerns. This integration reflects growing regulatory and ethical obligations in software design. Shared responsibility models further influence application threat modeling, clarifying which controls are provider-managed and which remain with the customer. For example, a cloud provider may secure physical hosts and hypervisors, but customers must secure application APIs, encryption, and identity. Misunderstanding this split can create gaps, with each side assuming the other is responsible. Threat modeling in cloud contexts must explicitly document responsibility, ensuring that mitigations are aligned to actual control ownership. Data classification influences how applications handle payloads at every stage. Sensitive classes of data, such as personal or financial records, demand stronger authentication, granular authorization, and detailed logging. Lower sensitivity data may allow more lenient handling. For example, logs of health data require strict retention policies, while operational metrics may not. Classification provides the prioritization mechanism for applying controls proportionally. Without it, applications risk overprotecting trivial flows while underprotecting critical ones. Identity and session management introduce unique concerns in distributed applications. Token issuance must follow secure standards. Lifetimes must be bounded, and rotation must be enforced. Revocation mechanisms ensure that compromised tokens cannot be abused indefinitely. For example, access tokens for microservice calls may last minutes, with refresh tokens bound to device identity. Threat modeling ensures that session assumptions are explicit, reducing risk from replay or theft. It transforms identity from a vague assumption into a well-defined control surface. Secrets risks are ever present in applications. Hard-coded credentials, environment variable leaks, and unsecured configuration files create silent vulnerabilities. Threat modeling identifies where secrets exist, how they are retrieved, and whether Vault integration ensures auditability. For instance, database passwords may be issued dynamically by a Vault with short lifetimes, preventing static exposure. By identifying secrets early, threat modeling ensures they are governed consistently, reducing one of the most common sources of compromise. Supply chain exposure extends risks beyond code written in-house. Dependencies, container images, and build pipelines must be evaluated as part of the model. For example, a malicious library imported into a microservice may compromise the application before it is ever deployed. Build system security, artifact signing, and provenance tracking reduce these risks. Threat modeling incorporates supply chain explicitly, ensuring that vulnerabilities cannot bypass scrutiny simply because they originate upstream. Event-driven patterns create their own attack surfaces, Message validation must prevent injection and replay. Dead letter queues must be protected against data leakage. For example, a message bus that fails to validate schema may pass malformed payloads into downstream services, creating cascading issues. Threat modeling these systems ensures that asynchronous workflows remain resilient against abuse. It acknowledges that events are just as critical as synchronous requests, requiring equal security attention. Server-side request forgery remains a high-risk category in cloud-native apps. When services fetch external resources, adversaries may craft requests that pivot to internal systems or metadata endpoints. For instance, a vulnerable API fetching image URLs may be abused to retrieve sensitive cloud credentials. Threat modeling highlights these risks and drives mitigations such as allow lists, request validation, and metadata service hardening. SSRF illustrates how subtle design decisions can create serious systemic risks if left unchecked. Misconfiguration risks often cause as much damage as coding flaws. Overly permissive cross-origin settings expose APIs to browser-based attacks. Wildcard roles grant more access than intended. Overbroad network access collapses trust boundaries. For example, allowing all origins in CORS headers may expose internal APIs to malicious scripts. Threat modeling explicitly identifies these risks, ensuring that secure defaults and least privilege principles are applied consistently. It underscores the importance of governance alongside coding practices. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The process for attack simulation and threat analysis, or PASTA, provides a structured framework for risk-driven modeling. PASTA unfolds in stage steps, beginning with defining business objectives and system context, then moving through threat identification, vulnerability analysis, attack simulation, and risk evaluation. Each stage validates assumptions and ties risks back to measurable business impact. For example, PASTA may simulate a token replay attack against an API and evaluate both technical consequences and regulatory implications. By aligning modeling with business outcomes, PASTA ensures that mitigations are not only technically sound, but also prioritized according to real risk appetite. Attack trees offer another useful visualization by depicting adversary goals and decomposing the steps needed to achieve them. Each branch represents possible attack paths, while leaf nodes identify specific actions or preconditions. For instance, the goal of steal customer records may branch into compromise API key, exploit injection flaw, or access misconfigured storage bucket. Attack trees make adversary thinking visible, allowing teams to analyze which paths are feasible, costly, or likely. They also highlight where defenses can block multiple branches at once. Written in text form, attack trees remain accessible, ensuring that the entire team understands both the threats and the defenses required. The MITRE ATT and AMP CK framework for cloud enriches threat modeling by mapping adversarial tactics and techniques to real-world detections and mitigations. ATT and AMP CK provides a shared vocabulary for describing how attackers achieve persistence, privilege escalation, or data exfiltration in cloud contexts. For example, ATT and AMP CK includes techniques like credential theft from metadata services, which can be mapped directly to mitigations such as disabling insecure instance metadata endpoints. Integrating ATT and AMP CK ensures that threat models are grounded in observed adversary behavior rather than hypothetical speculation. It also provides a bridge to detection engineering, aligning models with operational defenses. Scenario definition takes abstract threats and expresses them in plain language narratives. Each scenario outlines preconditions, attacker capabilities, steps taken, and expected controls. For instance, a scenario may describe a compromised contractor attempting to exfiltrate data through an exposed API, detailing what logs should capture the attempt, and how controls should respond. These narratives make threat modeling accessible to stakeholders beyond security teams, including developers, executives, and auditors. They also provide reusable building blocks for testing, training, and incident exercises. Scenario-based modeling ensures that threats are not only identified, but communicated in a way that drives action. Risk scoring transforms qualitative findings into quantitative guidance. Likelihood and impact are rated on structured scales, producing composite scores that rank threats. Rationale must be documented, referencing evidence such as historical incidents, vulnerability scans, or exploit availability. For example, an injection risk in a critical payments API may be scored as high impact and medium likelihood, yielding an overall high risk. Risk scoring enables prioritization, ensuring that limited resources focus on the most dangerous threats. It also introduces transparency, showing why certain issues were escalated while others were deferred. Control selection maps identified threats to specific safeguards, distinguishing preventative, detective, and corrective measures. For instance, SSRF risks may be mitigated with outbound request allow lists, preventative, API logs, and anomaly detection, detective, and emergency token revocation procedures, corrective. Each control must be assigned an owner, ensuring accountability. This mapping converts abstract risk into concrete engineering tasks, embedding responsibility into teams. Control selection ensures that mitigations are not only designed, but actively managed throughout the application lifecycle. Detection mapping strengthens the model by aligning threats with the specific telemetry needed to observe them. Logs, metrics, traces, and analytic rules are linked to each risk, defining how coverage is achieved. For example, replay attacks may be mapped to API gateway logs showing duplicate tokens, while brute force attempts may be mapped to metrics of failed logins per IP. Detection mapping closes the loop between modeling and observability, ensuring that threats are not only mitigated but detectable if attempted. It also provides measurable criteria for evaluating whether monitoring is effective. Model as code represents threats, scenarios, and controls in machine-readable formats, enabling validation within pipelines. Instead of storing models as static documents, Model as code integrates them into development workflows. For example, YAML-based threat definitions may drive automated checks for boundary enforcement or encryption requirements. This approach aligns with infrastructure as code, making threat modeling repeatable, testable, and version-controlled. By codifying models, organizations ensure that security assumptions evolve alongside applications rather than being forgotten in static documents. IAC policy checks enforce requirements derived directly from threat models. If the model dictates that all storage must be encrypted, policy as code engines can block deployments that omit encryption flags. If the model requires network segmentation, IAC scans can prevent wide-open security groups. Linking IAC checks to models ensures that mitigations are continuously enforced in practice, not just designed in theory. It embeds threat model outcomes directly into pipelines, creating living controls. Test design derives abuse cases and negative tests from high-risk scenarios. For example, if the model highlights injection as a critical threat, test cases deliberately submit malformed inputs to confirm defenses. Negative testing ensures that applications fail safely under misuse, validating assumptions from threat modeling. By linking tests directly to models, organizations ensure that mitigations are verified consistently. This makes threat modeling actionable, producing real test cases rather than theoretical documents. Validation exercises put threat models to the test through red team operations, purple team collaborations, or tabletop drills. Red teams attempt to exploit modeled weaknesses, purple teams validate both attack and defense, and tabletop sessions rehearse responses. For example, a red team may attempt SSRF exploitation to test whether modeled controls and detections hold. These exercises confirm assumptions, expose gaps, and provide feedback loops for continuous refinement. Validation ensures that models reflect reality, not just design aspirations. Residual risk documentation captures the threats that remain after mitigations, explaining why they are accepted, what compensations exist, and when they will be revisited. For instance, a dependency risk may be accepted temporarily if no patch exists, with monitoring and time-bound reviews in place. Residual risk makes explicit the fact that security is never absolute. It preserves transparency for stakeholders and auditors, ensuring that risk decisions are conscious and recorded. Decision logs preserve the rationale behind threat modeling choices, capturing assumptions, trade-offs, and references. These logs provide continuity as teams change, ensuring that future maintainers understand why certain risks were accepted or mitigations chosen. For example, a decision log may note that multi-region replication was deferred due to cost trade-offs, with compensating monitoring in place. Decision logs strengthen governance, preventing knowledge from being lost over time. Backlog integration ensures that mitigations from threat models are tracked and prioritized alongside feature development. Each mitigation becomes a backlog item with acceptance criteria and measurable outcomes. For example, implementing token rotation policies may be defined as a user story with testing requirements. Integration ensures that threat modeling outputs are not abandoned but drive concrete engineering tasks. It aligns security priorities with agile development rhythms, embedding them into delivery. Review cycles revisit threat models whenever architectures change, new dependencies are introduced, or incidents occur. For instance, adopting an event-driven messaging system may introduce replay risks requiring new controls. Regular reviews keep models current, ensuring they remain relevant in evolving environments. They also incorporate lessons learned from incidents, strengthening resilience over time. Review cycles transform threat modeling into a continuous process, not a one-off design exercise. In summary, structured threat modeling for microservices and APIs ensures that risks are identified, mitigations prioritized, and detections mapped. Frameworks like Stride, LindDUN, and ATT and AMP.CK provide structured perspectives, while tools like Pasta, attack trees, and Model as Code operationalize the process. By linking outputs to IAC checks, abuse case testing, and backlog integration, organizations ensure that threat models drive real outcomes. Residual risk, decision logs, and review cycles provide defensibility, making risk decisions transparent and auditable. Done well, threat modeling evolves from static diagrams into a living discipline, producing trustworthy applications that can withstand both design time flaws and runtime adversaries. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.